Hello and welcome to this first lecture on the flexibility method. In this lecture, we will start off by determining why we need to use indeterminate structures, discuss the different methods for solving them, and then hone in on the flexibility method. We'll discuss the theory and the concepts before using a solved example to bring all of that theory to life. Let's start. Before we begin looking at the flexibility method itself, let's first consider a few important questions. The first one is, how have we analysed structures so far? Throughout the previous lectures, we've determined support reactions and internal forces using the equations of equilibrium. This approach has worked well because the structures that we have analysed so far have all been statically determinate. So, what are indeterminate structures? Well, these are structures in which the number of unknown reactions or internal forces is greater than the number of available equilibrium equations. As we'll see shortly, this means that equilibrium alone is no longer sufficient to determine a unique solution. And this naturally leads to another question. Why do engineers use indeterminate structures? So, if they're more difficult to analyse, surely it would be easier to just avoid them? What we will see is that indeterminate structures offer several important advantages in terms of strength, stiffness, and robustness. And finally, how do we analyse indeterminate structures? So historically, there are two classical methods that were developed to solve statically indeterminate structures. The first one is the flexibility method, sometimes also referred to as the force method, and this is the method that we will be discussing in this series. The second is the stiffness method, also known as the displacement method, and I have a full series covering that method if you're interested. But in this lecture, as I said, we will concentrate on the flexibility method. We'll develop the concepts step by step before solving our first indeterminate beam and putting that theory into practice. So as we already mentioned, for statically determinate structures, the support reactions and internal forces can be determined using the equations of equilibrium alone. Let's consider the truss shown here. As you've seen in previous modules, our first task is usually to determine the support reactions, and once they're known, we can move on to calculating the internal axial forces in each member. The reason that this is possible is that the number of unknown components is exactly equal to the number of available equations in 2D. By applying the equations of equilibrium, we can obtain one unique set of reactions and internal forces. This is the key characteristic of a statically determinate structure. For a given loading, there is only one solution that satisfies equilibrium. So the key takeaway here is that for statically determinate structures, equilibrium alone is sufficient. For statically indeterminate structures, however, the number of unknown reaction components is greater than the number of available equilibrium equations. Let's compare this frame with structures that we've previously solved. By fixing all the supports, we have introduced additional reaction components. Therefore, the number of unknowns, in this case 9, is greater than the number of available equilibrium equations, which, as you know in 2D, is 3. If we apply the equations of equilibrium, we'll find that there isn't a unique solution. In fact, many different combinations of reactions will satisfy equilibrium. However, only one of those combinations will represent the actual behavior of the structure. To determine that unique solution, we need one additional condition, and that is compatibility. Compatibility describes how the structure deforms under load. The displacements and rotations throughout the structure must be consistent with the supports, connections, and continuity of the structure. In other words, the structure cannot deform in a way that violates its physical constraints. For example, in this frame, each of those fixed end supports prevents vertical displacement and horizontal displacement and rotation. These conditions provide the additional equations that we need to determine the unknown reactions. So the key takeaway here is that for statically indeterminate structures, equilibrium alone is no longer sufficient. We must also satisfy compatibility to obtain the unique solution. As we've just seen, indeterminate structures are more difficult to analyse because equilibrium alone is no longer sufficient. And this raises the obvious question: why do engineers deliberately choose indeterminate structures? So to answer that, let's compare two beams carrying the same uniformly distributed load. The first is a simply supported beam and is therefore statically determinate, meaning that we can solve the reactions and internal forces from equilibrium alone. The second is fixed at both ends and is statically indeterminate. Let's first look at the bending moment at the centre of each beam. For the fixed-ended beam, the bending moment at mid-span is approximately 67% lower than that of the simply supported beam. The continuity of the fixed supports allows part of the load to be carried by the moments at the supports, and this significantly reduces the bending moment within the span. Let's now look at the deflection of the centre of the beam. The fixed-ended beam deflects approximately 80% less than the simply supported beam, making it considerably stiffer. These two improvements have important practical implications. Lower bending moments can lead to a more efficient use of material, while smaller deflections improve serviceability and overall structural performance. And so from here we can take away that indeterminate structures can provide lower bending moments within span, smaller deflections, and a more efficient use of material. We've just seen that indeterminate structures can reduce bending moments and deflections. However, there's another equally important advantage. Let's begin by considering this determinate offshore jacket. Offshore jackets are commonly used to support platforms in the oil and gas industry. One of the most demanding environments for these structures is the splash zone. This is the region around the sea surface where the steel is repeatedly exposed to seawater and air as waves and tides rise and fall. This repeated wetting and drying creates the ideal environment for corrosion, making the splash zone one of the most vulnerable regions of the structure. So looking at this jacket, imagine that one of the braces within this region becomes severely corroded and loses its ability to carry load. Therefore, I've deleted it from the structure. Without that brace, the structure loses its only available load path. The forces can no longer be transferred effectively, causing the upper part of the structure to become unstable. Now let's compare this with an indeterminate jacket structure. Although the same brace has been removed now, the structure contains alternative load paths, so the forces are redistributed throughout neighbouring members, allowing the structure to continue carrying load despite the damage. This ability to redistribute forces is one of the major advantages of statically indeterminate structures. It improves the robustness and resilience and is an important consideration in the design of many critical engineering structures. And so the key takeaway here is that alternative load paths improve the robustness and structural resilience of indeterminate structures. We've now seen two important reasons why engineers often choose statically indeterminate structures. They can reduce bending moments and deflections and provide alternative load paths that improve the structural robustness. However, these advantages come with some trade-offs. The first is that indeterminate structures are more complex to analyse. As we've already discussed, equilibrium alone is no longer sufficient, and additional compatibility equations are required. Secondly, because the structure is restrained, support settlements can induce internal forces and moments, even in the absence of external loading. Similarly, temperature changes can cause thermal expansion or contraction, which may also generate significant internal stresses if movement is restrained. And finally, providing continuity often requires more complex detailing and construction, which can increase the overall cost of the structure. But despite these challenges, the advantages of indeterminate structures generally outweigh the disadvantages. And this is why continuous beams, rigid frames, and many other modern structures are deliberately designed to be statically indeterminate. So the key takeaway is that the improved structural performance of indeterminate structures usually justifies the additional complexity of analysis and design. So now that we've seen why engineers use statically indeterminate structures, the next question is, how do we analyse them? So, as I mentioned in the beginning, historically there are two classical methods that were developed, and they're summarized in this table. The first is the flexibility method, which is also known as the force method. As the name suggests, the unknowns are the redundant forces. The method is based primarily on compatibility, making it most efficient for structures with a low degree of indeterminacy. Consequently, it is used primarily for statically indeterminate structures. The second method is the stiffness method. It is also known as the displacement method. Here, the unknowns are the nodal displacements and rotations. The method is based primarily on equilibrium and is particularly efficient for structures with many degrees of freedom and can be applied to both determinate and indeterminate structures. Although these methods appear quite different, they're actually solving the same physical problem. Both satisfy the equations of equilibrium and compatibility. The difference lies simply in the unknowns chosen for the analysis. If you are interested in learning about the stiffness method in much greater depth, I've already produced a comprehensive lecture series that covers everything from the fundamentals through to complete MATLAB and/or Octave implementation. I'll include a link to the series in the description below. But for the remainder of this lecture series, we will be focusing on the flexibility method. We've now compared the flexibility and stiffness methods. So let's focus on the flexibility method and look at the overall procedure before we work through an example. The first step is to determine the degree of indeterminacy. This tells us how many redundant forces we need to introduce. Next, we select one or more redundant forces and release them. By removing these redundants, we obtain an equivalent primary structure that is statically determinate. Because the primary structure is determinate, it can be analysed using equilibrium methods that we're already familiar with. We then apply compatibility to determine the values of the redundant forces that ensure the original structure deforms in a manner that is consistent with its supports and continuity. And finally, once the redundant forces have been determined, we return to the original structure and use the equations of equilibrium to determine the remaining reactions and internal forces. Now, don't worry if just now some of these ideas seem a little bit abstract. The purpose of this slide is simply to introduce the procedure, and in the worked example that follows, we'll apply each of these one at a time, and you'll see how they all fit together to form a very straightforward and logical solution process. So now that we've looked at the general procedure of the flexibility method, let's apply those steps to a simple example. We'll consider this two-span continuous beam. It's subjected to a uniformly distributed load over the entire length. So the first step in the procedure, as you recall, is to determine the degree of indeterminacy. So before we do anything else, ask yourself, is this beam statically determinate or indeterminate? And if it is indeterminate, how many degrees of indeterminacy does it have? So we'll take a moment to count the unknown reaction components, and then we'll compare them with the three independent equations of equilibrium available in 2D analysis. So, as you've probably realized, this beam is one-fold statically indeterminate. It has one more unknown reaction that can be determined using equilibrium alone. And this tells us that we need to introduce one redundant force, and that'll be our next step. So now that we've established that the beam is one-fold statically indeterminate, the next step is to select a redundant force. Before we do that, it is useful to introduce the principle of superposition, which forms the basis of the flexibility method. The idea is quite simple. Instead of analysing the original indeterminate beam directly, we represent it as the sum of two simpler systems. The first system is a simply supported beam carrying the external loading. The second system is the same beam subjected only to the unknown vertical force By applied at the location of the removed support. When we add these two systems together, they reproduce the behaviour of the original structure. Before we proceed, we must notice an important property of the two component systems. Each of these structures has to be stable, and each of these structures has to be statically determinate for this to work. And that means they can each be analysed independently using equilibrium, together with beam deflection methods you already know. In the next step, we'll formally define the primary structure and introduce By as the redundant force that we need to determine. In the previous slide, we represented the original beam as the superposition of two simpler systems. Let's now introduce the terminology that we will use throughout this lecture series. The upper beam is called the primary structure. It is obtained by releasing the reaction at support B, leaving us with a statically determinate beam that can be analysed using equilibrium. The removed reaction is called the redundant reaction. Why redundant? Because it is the reaction that makes the original structure statically indeterminate. If we temporarily remove it, the structure becomes statically determinate and can be analysed using methods we already know. Of course, the real beam does have a support at B. So we haven't discarded this reaction, we've simply replaced it with an unknown force, By. The value of this redundant reaction is not known initially. Instead, it will be determined by enforcing the compatibility condition, ensuring that the combined response of the two component systems is identical to that of the original beam. Notice that both component systems are stable and statically determinate. And this is what makes the flexibility method possible. We replace one indeterminate problem with two determinate problems. We analyse each separately and then use compatibility to determine the redundant reaction. Now, as you've seen here, I chose By. Could I have chosen something else? Yes, absolutely. But only if that redundant force would have given me stable determinate systems. We'll discuss this later. We've now identified the primary structure and the redundant reaction. The next step is to determine how each of these contributes to the deflection at the location of the redundant, which in our case is point B. Let's begin with the primary structure. The primary structure carries the uniformly distributed load. Since it is statically determinate, we can determine the vertical deflection at point B using any of the methods that we've already learnt. For example, double integration, Castellano's theorem, the unit load method, or virtual energy, or simply by using beam deflection tables. This isn't our purpose here, but you will find that for this beam, the deflection at point B is 5WL to the power of 4 divided by 384 EI. As expected, the beam deflects downwards under this applied loading. However, as we know, this alone does not represent the full beam. We need to consider the second structure that makes up the full original beam. Now, here we face a slight problem. We don't yet know the value of the redundant reaction By, so we cannot calculate its deflection directly. Instead, what we do is apply a unit vertical load at point B. Why do we use a unit load? Because we know how to calculate the deflection produced by 1 unit of force. Once we know that deflection caused by a unit load, the principle of superposition tells us that the deflection produced by any other force is simply proportional to its magnitude. So if a unit force produces a deflection of delta R1, then the actual redundant reaction, By, produces a deflection equal to that delta R1 multiplied by By. For the unit load, the deflection at point B is PL cubed divided by 48 EI. And since P equals 1, this just simplifies to L cubed divided by 48 EI. Now, this quantity is called the flexibility coefficient, and it represents the deflection at point B produced by a unit force acting at point B. But again, this is terminology that we'll cover later. So finally, let's return to the original beam. The distributed load produces a downward deflection, while the redundant reaction produces an upward deflection. But what is the actual deflection at point B? Well, we know that it must be 0, because point B is a support and it can't move vertically. And therefore, the compatibility equation becomes delta 0 minus delta R1 multiplied by By equals 0. This equation contains only one unknown, the redundant reaction By, which we can now determine. And this is known as the compatibility equation. We've now established the compatibility equation. The next step is to simply solve it for the unknown redundant reaction. We begin with the compatibility equation that we just found, delta 0 minus delta R1 multiplied by By equals 0. What we need to do is substitute the expressions that we've obtained for the two deflections. And this gives 5WL to the power of 4 divided by 384 EI minus L cubed divided by 48 EI multiplied by By equals 0. Notice that both terms contain EI. This is exactly what we'd expect because both deflections are calculated for the same beam. We can now rearrange the equation to make By the subject. And after simplifying, we obtain that By equals 0.625 WL. This is the value of the redundant reaction at support B. Before moving on, it is always good practice to perform a quick sense check. First, we'll check that the units are correct. The distributed load W has units of force per unit length, and multiplying by the span L gives units of force, which is exactly what a reaction should have. Second, the direction is also sensible. We assumed an upward redundant reaction, and the solution is positive, confirming that our assumed direction was correct. And now, with the redundant reaction known, the flexibility method has done its job. The remaining support reactions and internal forces can now be determined using the equations of equilibrium alone. So from this point onwards, we're back in familiar territory once we've determined the redundant reaction By. The flexibility method has enabled us to determine the redundant reaction. The remaining support reactions can now be found using equations of equilibrium just as we would have for any statically determinate structure. So I'll not go over this in detail because you already know this, but I first applied horizontal equilibrium, then equation of moments around A, and finally I applied the vertical force equilibrium. We will notice that the reactions at A and C are equal, which is exactly what we expect because the beam and the loading are both symmetric. We can observe that compatibility was used only once to determine the redundant reaction. Once the redundant reaction was known, all of the remaining reactions were obtained directly from equations of equilibrium. This is one of the defining characteristics of the flexibility method. We use compatibility to determine the redundant force or forces, and then we return to equilibrium to complete the analysis. And let's just finish by revisiting the flexibility method procedure. We've now worked through a complete example, so each of these steps should hopefully make more sense than when we first introduced them. We began by determining the degree of indeterminacy, and that told us how many redundant forces we need to introduce. We then selected the redundant force, removed it, and created the primary statically determinate structure. Because the primary structure is determinate, we were able to determine the deflection caused by the external loading and by a unit redundant force using beam deflection methods that we already know. Next, we applied the compatibility equation to determine the value of the redundant force. And finally, once the redundant force had been determined, we returned to the equations of equilibrium to calculate the remaining reactions and internal forces. This is the complete flexibility method procedure, and it is the same sequence of steps that we'll follow regardless of whether we're analysing beams, trusses, or frames. In the next lecture, we will apply this procedure to statically indeterminate trusses, where the same principles apply, but the calculation of flexibility coefficients is slightly different. Thank you for watching, and I'll see you in the next lecture.